Well, hello everyone. That's right on 5. I feel super anally retentive, like watching my watch till 5 o'clock. I don't know what else you're supposed to do. So, welcome back. Yeah, week 2. You only get me for 8 lectures. I had a little look at the schedule the other day and went like, oh God, it's only 8. But we're nearly through. So you get me for 3 sections. So we're nearly through section 1. Then we'll get on to section 2 and then section 3 later. But you have a break in the middle where Amy Chan's coming in to talk to you. So she's a mathematician who's been out in industry. You'll get her perspective seminar. That's super interesting, especially depending on what your career aspirations are. It's really good to hear about, like, here's a career in mathematics. That's, you know, ask lots of questions, because like when you get these people in, it's like, you know, you should really try and pull some information out of them, because you don't get many chances to do this. I knew it was always, for me, when I was going through, it was a bit of a mystery about, like, what do you do after? Because, like, I don't know about you guys, but when I started doing mathematics, I didn't do it with the idea of getting a career. I did it because I was interested in maths. And it's like, you get to the end, like year 4, and you're starting going, oh, I should probably worry about that stuff at some point. So getting an idea of what it's like on the outside is a good thing. You got me too. If you have any questions for me, just ask away. Cool, so that's it. He only had a little bit of housekeeping. He's online, but I'll just say it for him, unless he wants to jump on. He's going to send a message with instructions for the big homework. There's going to be a short video accompanied with the message. The homework has 4 submission forms. Each one's a Jupyter notebook, and the notebooks are now stable. Hopefully that covers what he wanted to say, but he's going to send a message about that. I hope you've all started the homework. Has everyone started the homework? Yeah. Oh, that's great. Some people are looking sheepish, so should start early. And you get, like, one of the things, like, I guess this is another thing you can take away is, like, get feedback early on where you're going with things like this. It's like, it's a different type of course. Like, if you can get a version in and get help early and iterate on it, that's kind of what it's more like working as a software developer. You don't get it right the first time. You get it right after trying lots and lots and lots of times really quickly. Little bit of advice. So, like, if you can get in early, don't learn what you don't understand really quickly and then get help, do that. I'll hopefully help. Hit me up. They've got the EdSTEM thing. You can send me an email if you've got mine. I don't know, do you guys have a link to my email? Because I don't mind you doing that either. I'll send it after the lecture if you don't have it anyway. I'll probably regret that, but I'll give you a fake email. So it's fine. I'll give you Andy's. Cool. Okay, so section 1. And we're going to go on to section 2. So section 1's just the basics. We're starting just about variables, arithmetic, all these things. You know, we did a couple of examples. We're going to do a few more examples. That'll be like the first bit. Hopefully by the break time, I'll get through section 1. Then we'll get started on section 2, which should be more interesting, depending on your bent. Like, this is more like standard CS curriculum stuff where we're going to go into analysis of sorting. So, like, as a first example, and then we're going to go through more data structures, basic data structures you need to know. And then I'm going to talk, this is bits kind of like exciting for me in a nerdy way, about like professional development stuff in mathematics. Is not a thing you usually do, but get to talk to you about, like, the tools you'll probably use. So, like, have you guys, trying your homework, have you been using VS Code or using some other editor? Having success, or can you see the point of it? Sort of, maybe not. Have you used Git before? Who's used Git before? A couple of you. Yeah, this will be fun, because, like, Git is renowned for making people want to cry when they start learning it. It's horrible, but when you get over the learning curve, it's super useful. And the unfortunate thing is, like, everybody in industry uses Git, so, like, you don't get a choice. You have to learn how to use it, and it's actually fine. We'll be gentle, and the best place is you can practice here. I have stories I always want to tell when I'm in these lectures, and I go, like, maybe I shouldn't, but at a place I used to work at, we had an intern who force pushed to master and blew everything away. This is a thing you can do. So, like, if you do that when you're in uni, that's great. Like, it's just an assignment. If you do it when you're out. Oh, you've got a question? Did I get an offer? It was actually even weirder than that, because I won't say too much because I'll give away where I was working. But yeah, it was a strange situation and it was bad. It was very, very bad. But we managed to save it. And it's one of these things about Git, is that it's a distributed system. So It's actually quite fault tolerant if you use it right. We could actually recover and it wasn't a problem. Yay for Git. Okay. No, someone, we've got a comment. I'm actually going to try harder to watch the comments come up. So I never use Git. I literally had to watch what is Git for instructional video. Yeah, so we're going to go through all that. Basically, the idea is Git is a distributed database for code. So you always have this problem of controlling source code and who gets it and how you edit it. So I'll go through that more in detail, but that's what Git's for. It's actually going to seem really arcane and strange if you are using it on your own, because it's like, what am I using all this infrastructure for? It's more when you're working in a team with lots of people and you're all trying to manage the source code so you can deploy it and keep track of changes. So you're not scared of changing stuff so much. That's what it's for. But in practice, when you're learning, it's like a little bit of a terrifying thing. So we'll be really gentle. You learn it here. Doesn't matter if you break stuff. The fact you're using it is really positive. Like one of the things I look for when I Git interns and stuff is like, oh, do they have a GitHub repo where I can go and look at stuff they've done, even if it's just for uni assignments, get an idea of what they've done before. So like, it's actually nice for transparency when you go and try and get a job if you have this stuff available. So the fact we do this for the course is kind of cool. Cool. That's what we're up to. So we'll start off unit 1. I'll just review as I like to do, so I remember what I was doing. We did basics with this thing that's like reservoir sampling. I didn't say that. I won't say too much about that, but it's fun application, going introduction, blah, blah, blah. Representation, how you do low-level addition. You know, this may or may not be interesting to you. It's good to see it at least once. It's like, again, it's like, I don't expect you to know this stuff, but it's cool to have seen this stuff once and understand what's going on underneath. A little bit about bit shifts and boring stuff from that. Hello world and Julia, and we went through square roots. So this is getting more towards stuff that's useful as a mathematician working in software. It's like, how would you actually implement a function? How would you implement a function that does something you might want to do as a mathematician, like finding a root? And there's this really interesting thing. So the answer for this one is like, there's actually lots of variants of how you could implement square root. I just showed you a very simple one, Babylonian algorithm. The one that would be implemented is actually quite sophisticated. You can go off and look at that. I don't actually know what they do most of the time these days. It's just like, this is a nice abstraction we can use. But the interesting thing as a mathematician is, and I'll talk about this again today, is that these things you're doing when you're learning calculus, you know, like what's the actual intuitive definition of a derivative? It's like instantaneous slope at a point. You use that definition to derive an algorithm. So you're doing successive linear approximations, solve where the linear approximation hits 0, resolve again, resolve again. So this come up again when we're talking about factorial, that I find this super interesting. Come back again and again when we do numerical derivatives, ODEs, and integration, quadrature methods, that these sort of weird technical definitions you use to derive, so like you can do these epsilon proofs of what a limit is to derive a derivative, that actually gives you an algorithm, and that's how a lot of these algorithms are built up from the beginning. A little talk about big ants. Yep, so that's Newton's method, blah, 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 blah. I quickly gave you this overview of the Quake3 algorithm. I'm not sure if I did a good job, but basically there's a point again, if I'm going to make a didactic point, like what you should learn from this is, again, it's just Newton's method, which is this line here, you know, just do Newton's method. But, and then there's some clever hacks above that. So I'd put this in the category of this as a clever hack. So my lesson to you guys would be like, if you're going to do clever stuff, please say what you did so other people can understand it. You never are a solo contributor for this stuff. You're always working with other people pretty much. Even more so if you do open source stuff. So talk about that in section 2 too. It's one of the things I like. One of the other things you should learn about is like, there's a whole bunch of licensing stuff with software, and most people who come out of uni education have no idea. So it's good to know. I won't give a comprehensive overview because it's like I'm not an expert on that one. Okay, any questions on what we've done so far? That's my little quick review of where we're up to. I won't do that again for this bit. Happy? Cool. Okay. So what's the useful story here? So this is another one. So factorial function. This, I hope you're all familiar with factorial, definition of a factorial. It's like we're going to go factorial n, which would usually be I was completely prepared. I should have started this up for you guys. So like if we were going to go, 10 to the factorial, that's what you do in mathematics. And usually it's like 1 times 2 times 3 times 4, blah, 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 up to 10. That's a useful thing. It's also a thing that grows very, very quickly. So how would we implement this? So there's a built-in one, nearly always. So I always harp on about this. Like if you're confused, go to grepl, type in question mark, check what the function does. It's even got a link to Wikipedia, believe it or not. So factorial of n, if n is an integer, factorial is converted to an integer, reverted to at least 64 bits. That's kind of interesting, that bit of documentation. Note that this may overflow in n if n is not small, but you can use factorial big N to compute the result exactly in arbitrary precision. So, factorial is the thing that grows really, really quickly, right? Like, so we can do factorial 10, no problems. It's a very big number, but this thing grows like crazy. So factorial 1, 2, 3, 4, 5. So do a list comprehension here just to see what like how the first 10 grow. Growing very, very quickly. We've got some sort of semi-nifty examples over here, depending on your perspective, I guess. So this is a little bit weird, but usual syntax when you're writing Julia would be like this, 10 times 2. But again, this multiplication operator is a function. This is just syntax. You can actually call multiply like a normal function with a tuple like this. Man, that's a lot of help. I'm not going to bother going through that. So this slightly weird syntax, we can go times, and then we have an iterator. So remember, this will list out all the numbers from 1 to 10. It's an iterator. So if I do this times, and then these funny little ellipsis is called a splatting operator. So what that will do is take all of the things in the iterator and put them one after the other into the function. So that is the same as factorial. That's kind of nasty, but it's a good little bit of syntax to see. That's the thing. You might want to use that. Another one is this accumulate. So what this will do is do them in order. So it'll apply the multiply operation, one after the other, after the other, after the other, and keep accumulating the result. So it actually makes an array. So calling last on that will just take the last element of the other array. So that's the same, but it's kind of a silly thing to do. Depends how clever the Julia compiler is. I think it depends. I don't know. This would be one where you'd go and look at code lowered. Like it might optimize a way that it doesn't need to store the 1 to 10. But if you're like, it's only 10, like factorial is going to blow up really early, which we'll see in a minute. Like for this one in particular, no, because it's like they're so small, it doesn't matter anyway. But in general, if it's allocating that array and then just taking the last one, that's an allocation you don't have to do. You're making all these elements just to take the last one, which is kind of a silly thing to do. General thing to do is just use the built-in one if there is one, if one exists, because that will be optimized. Make sense? Yeah. Cool. This is more, there's a million ways to skin a cat. I hate that expression because it's disgusting, but lots of ways to skin a cat. You can see a bunch of different things. Usually you write something bad like this when you're panicking at midnight trying to do your assignment, you'll come up with the strangest way of doing this function, but if you're me anyway. So you see, just to see some more syntax is the idea. So last is actually more useful bit of this syntax. It's like it'll suck off the last bit of an array. Same as you can do first. This won't give you the factorial, it'll just give you 1. And take off first. First, last. Useful things to know. Okay, this one last one is bad, but I'll show it to you anyway. You guys have come out of doing lots of scripting stuff in Python. One of the things that's like a bit of a barrier is like, you probably should wrap everything in functions for Julia to make it fast. So like if you have a homework assignment, say, where it says trying to make a thing fast, if you do it in global scope, like it's just a bit of script and it's not inside a function, you'll have to do something funny. Like, I don't know if you guys have seen this yet. I'll copy this one across. Anyway, if I try to do this, fd equals 1, and then for I in 1 to 10, fd times equals I. Let's tab that out so you can see it. What's going to happen when I press enter here? Anyone want to have a guess what's going to happen? Have they tried this? Has anyone run into this bug yet? Bug feature? You're nodding your head?
It doesn't recognize FD as a variable like that.
Yeah, so, oh, maybe it did in this case. That's interesting, but it depends on the actual type of the thing underneath. But sometimes you'll see that you have to do this global stuff where you're saying something's a global variable, and this is about scoping rules. This will be like your first example of scoping rules. Putting the little global in there so it doesn't crash out because it knows that this variable's not defined. Usually for those iterators, inside the iteration bit, it's scopes only, variables only have that scope, depending on the type of the thing. It's a little bit confusing. So if you see these little global things here, it's because it's a terrible script. When you're going to do stuff for yourself, please write everything in functions. If you're going to do this, you do something like function my factorial of n, etc., etc. You know, all that stuff that's just in line by line, please do it in a function, return it. It will make Julia faster. The reason for that is to do with type inference. When Julia compiles stuff, it tries to work out the types of everything. If it can't figure that out, if anything's a global, basically, that will be one of the reasons it will fall over and go slow, because it can't do specialized code. When we saw that code lowered, I don't know if you remember that from a lecture ago, that stuff will be a mess. If it can't figure that out, it'll be very, very long. Whereas if it's all tight, it'll be fast. So that's just a little, don't worry too much about it for this one, just a hint for you guys. So they all should do the same thing. That global thing's just saying something's a global variable. Sometimes you do have to do it, sometimes you don't. Talk about that later. More of that stuff, more of the scoping rules will come up in Andy's section. It's a bit more advanced. Not going to worry too much about it. Just if you see it, that's what it is. Okay, now one of these ones that's like, sometimes it makes people's heads hurt, but functions can call themselves. Like, is a really useful property for a function to have. For a mathematician, math student, like recursive definitions of functions are supernatural. Like, you guys would look at this one here, we don't have a line number, but n factorial equals n times n minus 1 factorial. So it's got a definition of factorial in it itself. For n equals 1, 2, 3, 4, that. Otherwise, it equals 0. That's how you do it in maths. You know, you'd reference the function itself in the definition, and that's fine. You can have this type of recursion. You can do that in programming languages too. It's super useful. Some algorithms, which we'll come up to when we're getting into the next section, they're actually a really good way to make really high performance algorithms. So really natural. Some people have a bit of a mental barrier. So things calling itself, it's a bit weird. I think, is it worth me belaboring that, or we can just look at it? So what we're going to do is my factorial. This is basically just exactly the same as this definition. So we have a statement that if n equals 0, so that's that case, just return 1. Otherwise, return n times my factorial n minus 1. So it just calls itself with the argument decremented by 1. Go again until it gets down to 0. So hopefully, and then it will go back all the way up. So we've got a bit of logging here. Let's just copy paste this into a REPL thing, because this one's more interesting, I would say. Okay. So what this guy's going to do, we've got a bit of logging that's going to, I'm calling my factorial with $n. So that's the string interpolation syntax. So if you guys, if I say string interpolation, you're going like, yeah, what are you talking about? Or is that okay? Not okay? Good. That's a good thing to know. So I'll just enter that. So if I go x equals pi, y equals $x everyone, it's going to take the variable in x and put it into the string. That's right. Putting the string into that thing. That's what we're going here. So what this, if we go up to the my factorial function, it's going to print out calling my factorial $n. It's actually, because I'm pedantic, I'm going to put a space. Oh no, it's calling that function. I won't change that. I was going to get annoyed that there wasn't a space in there. I'll try not to get too pedantic. So if I call it with, hopefully, let's just go through it. If I call this guy with 0, we're going to hit this one first, and we're going to return value is going to equal 1. It's going to print line. I'm returning from my call n factorial with ret values. If n equaled 1, we're going to skip past this guy. Return value is going to equal n times my factorial n minus 1. So then in here, in this little part here, it's going to call itself with 0, go get 1, come back out. Hopefully that makes sense. So if I do it with 0, should go 1, 1. It's going to go calling my factorial 1, then it's going to go calling my factorial 0, then it's returning on the way out. So it's going to recurse down 2, 1, 0, 0, 1, 2. That's, if you looked inside the function, that's what it's doing. So, woo, lots of stuff, and gives us the same answer. So it's going to go 10, 9, 8. So it's going to call itself 10 times, return all those values, sum them, multiply them together. That's a recursive function definition. We can also do this as a bit of a clever one-liner. Can't drive my mouse. So this is more of it. So we can do the same thing. This is a ternary operator. You're going to go if n equals 0, return 1, otherwise times n times my factorial n minus 1. Cool. Do the same thing. And actually, this is to do with, we'll get these two. But interesting thing, I won't go through this, belabor it, but interesting thing is if we have this one where it's this ternary one, and we have this one where it's more long-winded, LLVM actually produces the same code for both. So what it's doing underneath, so I was saying about like Julia's compiler is fairly clever. It goes down, makes this machine stuff that can execute in a nice quick way. These two different functions define these two different ways will actually produce the same LLVM, produce the same machine code on the same CPU. Interesting, maybe not so interesting. I think it's cool. Yeah, you can verify that yourself, I'd say. Okay, now, again, talked a little bit about big ints, again, because it's useful, interesting that, you know, it's very easy to do things in mathematics that will get bigger than 64-bit. Like, it's kind of straight, especially for integers, it's really, really easy. We talked a little bit about how you do that. Whole idea of this next little bit of work is we're going to say, how big can we get? Anyone want to have a guess if they haven't read the notes? If you've read the notes, that's cheating. How big before do you think we run out of precision with 64 bits? Factorial. No one's brave.
20.
What's that?
20 rounds.
20? It's a good guess. Anyone? Gee, I won't keep playing that. Yeah, that's actually a good guess. So how we could do it is we can look at Stirling's approximation. Has anyone come across Stirling's approximation before? If you do physics, if you do StatMech, is that where you've seen it? Yeah, it's there. Mathematically, it's super interesting because it's a truncation of a divergent series. So you do a series approximation that's actually divergent, cut off the infinity bits, and then you're left with something that still works as a good approximation. I don't understand how that works. Some of you guys can go off and do a PhD and tell me in a couple of years like why that actually works. I don't understand, but It's very, very weird. And of course, because it's strange, physicists like it. They use it all the time. Okay, so I don't know how, this is Stirling's approximation anyway. So if you want to approximate factorial, it's this square root 2 pi n to the n on 1 plus 2 e to the minus n. Little bit of, I won't go too much about this one. It's just like showing this approximation is okay. Yep. So another thing, a little thing to point out is you would have seen this with gamma. You can get math constants e. If you want pi or e, pi is actually in there. You don't have to go math constants, but any of these other weird ones like Mascheroni constant or exponential, they'll be in there in math constants. Anyway, you can do a little numerical experiment over these 10 to see that it's okay. It's actually a pretty reasonable approximation. So using Stirling's approximation. So I talked about this before. If we wanted to see how big we can go, we can do this. Yeah, I don't know if that's super interesting, but so I guess the point here is like, if you have an unsigned int, you can go further. We saw all this stuff before. If you've got a signed int, you're going to get half the range. What we want to know is show the type max of the thing we're interested in. So type max of int 64 is a very, very big number. We've got the same one there. If you've got a uint, you get a little bit further. Interesting if you're using, as I said, we haven't talked too much about floats. That's in section 3. I'm going to come back to that. Type max of a float 64 is actually infinity. So in floating point, because you're trying to represent the reals, you get infinity minus infinity. You also get an n as special values. We'll come back to that though. Just a thing to know. So here's a little bit of code that's going to go through and find out what the maximum is. So the limit is going to be type max n. Use Stirling's approximation until it's less than the limit, then print it out. So this guy guessed it perfectly, 20. I thought it was 23. I'm disappointed. I thought it was around 23 for some reason. But anyway, that's a little bit of code. You can run through it yourself. I don't think it's super interesting to go through it in super duper detail. Again, this funny little global thing to make sure you in scope. Yeah, so we can actually just like, we can do all this analysis, or we can just try it. You can go factorial. It should die in a safe way, if you can spell. Factorial 20 is fine. Factorial 21. And it even gives you a nice error message where it's saying overflow error. 21 is too large to look up in the table, which is interesting because it's saying it's giving you a bit of a hint about implementation because it's saying it's looking it up in the table. So it's not even doing anything fancy here because there's only 20 it can do for this type. So if you go look at which method is getting dispatched in Julia for, as we did in the notes before, you can go look up the code, what it's doing. It must have a lookup table that it just goes through because that'll be much quicker. So can't do that with that type, but we talked about big ints. You can do no problem. You can do whatever. You can until you run your computer out of RAM. Like big numbers if you want to do them. So that's the use of that type, but it's much, much slower for normal integer things you might want to do. There's a penalty to it, like things like multiplication will be much, much slower with big ints. Yeah. Okay. So it's kind of, you will like, if you do go too crazy with a big int, you know, your computer will sit there running forever and fill buffers up with memory if you get big enough, but that's a very, very big number. Cool. Okay, so the thing you might want to do as a mathematician is you go, what does factorial mean if you use a real number? What's the extension of factorial to the reals? What will Julia do if I try and do that, it'll go, it's a method error because everyone who writes the Julia code is very precise and lots of them have maths backgrounds. It's like, it doesn't make sense to do factorial. One of these things, I showed you a log table book. One of these things is like, when I was an undergrad, I was starting to phase it out. They actually used to have courses on special functions. Has anyone ever heard of that? It's like, sorry? Oh, there is still a course on this? Okay, yeah, it's like, it used to be part of your undergrad. Like, probably like a decade before me, there'd often be a maths course on special functions second year. Like maybe instead of this course, you go and learn about Bessel functions and all these crazy things that you're going to come up. And one of these is the gamma function. Numerical methods have sort of killed them. Like you don't need to know all this stuff so much. It's interesting if you go off to pure maths, you'll see it again. But in terms of everybody needing to know it, it's not so important. So if you got, again, using special functions module, you can do the gamma function at 6.5. That will be no problem. Okay, and the gamma function has this funny definition in terms of a definite integral from 0 to infinity of x to the power of z minus 1 e to the minus x dx. Okay, so we've got a little bit here. This is going to come back again. This is the bit I actually wanted to make a point about, is that these definitions from your elementary calculus come back. So if you're going to implement the gamma function, how would you do it? And the way you can do it is just taking this integral. So like, if you look at the like when you learn basic calculus, you go like, what's the definition of an integral? And you go like, oh, it's this Riemann sum. So I drew a little picture of a Riemann sum, just in case you can't remember it. Spent too long. Basically, this idea that you just sum up these, an integral is an area under a curve. So you just get all these little boxes that sit on the curve. And you just take all these guys and you sum them up. And you take the limit as delta x goes to 0, you just do more and more little boxes, and this approximation will turn into the definition of an integral. This is actually a numerical method for doing integrals. It's like, it's the basic one, right? You guys done this before? Am I preaching to the choir? And well, you can tell me what's wrong with the way I've done this version of integration. Like, anyone see an immediate improvement? You're making a bit smaller as one, yeah, definitely. And you could take a different kind of average. You could do a weighted average. If I'm just thinking of this like geometric, yeah, I got Felix on the chat, is a good answer. So one thing you could do is like, I've lined these up, the boxes on the side, you could do a little trapezium everywhere. So that cuts off that top corner. So that's trapezoid's method. What would be the next extension of that? Yeah, so fit splines, fit higher order splines. We're gonna come back to that. It's not always a good idea. Sometimes doing this works better, which is interesting. Anyway, so I'm glad you're all familiar with that. You've all got intuition about how it works. Maybe I can skip over it a bit then. So you can basically, here's a little simple implementation of doing the dumbest sort of integration on a trapezoid method. And you can show that you get something pretty similar. And as you refine the mesh, as you make delta x smaller and smaller, the error will get smaller and smaller, and you get a better approximation. So there's a little bit of maths. The idea is like, what we want to show here is it's a continued. Why would you? This is just like an eyeball sort of intuition thing of like, why is this thing related to factorial? And it's like, oh, you can actually go through this, break up, do the integration by parts, blah, blah, blah. And you can show that you end up with a recursive definition of the gamma function that's the same when it hits the integers as the other. So that's why you can sort of think of it that way. And you can show that this first one equals 1. So cool, it works like, it should give you the same answer, which is this next little bit of code as we go through. That if you do the gamma function versus factorial, that's just basically that little bit of code. I think that's, I'll just run that just to verify. I won't because my mouse isn't working, but basically you get the same thing on the things bar some floating point stuff. The thing to notice though, that is at some points the gamma function is not defined and you're going to get these poles. Cool. It's just a little thing. I think the interesting bits there is about, you know, as I said at the start, these little definitions from basic calculus actually derive algorithms, and most of them work this way, that if you want to come up with an algorithm for how you approximate this function, go back to your basic definitions, think of a crude approximation of that. It's kind of how most of them work. Cool. Good. Any questions? Happy? Never want to see factorial again? That's good. We'll get through. Okay. Last little bit. So it's when you're dealing with programming languages, you know, the human part of the loop is like putting strings into a computer. So I keep saying strings. Strings is a set of characters, you know, that you put into a computer. When you're writing a program in a text editor, all these IDEs, they're just text editors. You're just putting strings in. The computer, the programming language takes these strings, parses them into some syntax it can evaluate. That's basically how all programming languages work. So you can't get away with knowing a little bit about strings. It's a little bit dry, but it's good to know. Good to know a bit about them because they'll come up again and again. You can't get away from it. So we'll just, again, I'll copy some stuff across. So we've got a string. We can go length of my name. What do you think that will say? Anyone? It's 5 because it's 5 characters long. So in Julia, this is like an array of characters. This is a string. We can also do size of, did I mention this or did I brush over this? So if you have a data type, you can get the size in bytes of that, saying for a particular string there. So it's the size in bytes of the canonical binary representation of a given data type T, if any. So that'll bite you with objects later on. That's for later, but don't worry about it too much now. So if I run size of my name, so the length of the array was 5. We also get the size of the array in bytes is 5. So it's 5 bytes. So each character is 1 byte, 8 bits for each character. That's kind of it. Yep. So we can go first, my name. J. So it's actually a different data type here. So type of first of my name is a char, type char. That's a little bit different. In the lecture notes, they're giving, instead of doing first, they're doing just another little thing you can see. You can do begin. You can also do end, you know, first, last, begin, end. You can do all this stuff. Thing to see there, and again, in Julia, if you want to do join 2 strings together, they've shown in Python it's a plus, in Julia it's a multiply. Whatever. Doesn't make sense. You can call it whatever you want. So if you go my name times my name, Janet, yeah, that's how you join 2 strings together. Okay, so how, again, going to the bits representation of how things are represented as data types. This is ASCII. So each one of the bytes is translated to a character, vice versa. They start at 32. There's a little bit of code here that prints out the ASCII table for you. So maybe this is relevant. Just did that bit. Maybe not super interesting. So again, just syntax. When I said this first, my name equals J. So that's false. It's not the same as a string. If you wanted to have a char, type char, you do these quotes. Equals means is this thing equal to this thing, just in case I haven't said that enough. Okay. There's a fixed offset between uppercase and lowercase. So easy way to do that is just, you can look at the difference between the two. So little challenge thing that's kind of not much of a challenge is if you wanted to implement something like uppercase, how would you do that? I'll leave that for you. This bit, okay, that's just strings. I just wanted to say about strings really, really quickly. I think the second bit's more interesting. This is like, does concatenating arrays work similarly? No, because you want to multiply arrays. I just got that question in the thing. So you have this problem with arrays. This will come up again later. If I do that, you know, there's a method error because they're the wrong shape. Can you actually multiply? If I think of these two things as vectors, can I multiply like a row vector by a row vector? Does that even make sense? What would I have to do if I was going to do that? Yeah, you can do an inner product if I take the transpose, or I can do an outer product if I take the transpose the other way. So you kind of don't want to overload the same string. Yeah, you can't, you don't want to overload that multiply operator for arrays. If you want to concatenate arrays, again, you got to worry about the shape of these things, like are they row vectors or columns? So you actually get vcat or hcat. So you go vcat 1, 2, 3, 1, 2, 3. You end up with that one. You end up with hcat. They go that way. Okay, sorry, sideways thing. Okay, so we're going to look at an example of string manipulation. So we're going to use two funny libraries here, HTTP and JSON. Who's familiar with JSON? A couple of people? You're going to be after your assignment because a bit of part of it's like looking at some JSON. I'm pretty sure that's one of the questions. Is anyone up to that yet? No, maybe it's one of your tutorials. Anyway, JSON's JavaScript object notation. I'll go through that later, but it's like everything you see on the internet, like your IPython notebook is really a big JSON file underneath. They're everywhere. And HTTP is a way of doing web requests in Julia. So what we're going to do, which is kind of dangerous for a live demo, we're going to go to a website and download all of Shakespeare. So let's see if that works. It's like internet should be working, so this is good. We're doing a thing called a GET request. So you go, it's one of these web APIs. So we're going to go to this address, which is ocw@mit.edu. There's some lecture notes, th.shakespeare.txt. And so we just downloaded in data a whole bunch of Shakespeare, which is kind of crazy. Someone's whole life work, dozens of books, really quick. It's actually kind of small. So what we're going to do, if you look at type of data, it's a HTTP message response. So what we're going to do is we're going to turn that into a string. So copy, paste, copy, paste. So I'm too lazy to type. If you looked at data, so it's a little bit nasty of like giving a hint about stuff coming up. As we talked about, you're going to have more and more complicated data types come up in Julia. Data is this type of HTTP messages response. So inside the HTTP module, there's a special data type of subtype messages, subtype response. And inside that, there's probably some stuff. There's a body, there's headers, requests, status, and version. So body, headers. Oh, no, it's already been consumed. cheating on me. Have to do it again. Data.body is this big array of uints that came from the internet. So it went to the internet, please give me some stuff. Stream of bytes coming in that are these uint ones. These are actually, you can turn these into a string. We know you need to know something about the type of data you're going to get to be able to interpret it. I know that this is a bunch of strings, so I'm going to call string on this to turn it into a big string. So that is Shakespeare. So this is a big long string of Shakespeare. So it has, 5 million characters. Okay, so there's some other stuff that was in that request thing, if you care. So there's headers. So this is all internet stuff, like so keep alive the connection, content length, class modified, e-tag, blah, 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 blah. I'll just let you see some of this stuff so it's not a surprise when it comes up later. So vector, there, blah, blah, kind of nasty. Okay. Request. So that's going to, what did it turn my request into? It keeps the record of that. And status 200. Is everyone familiar with the web codes? Have you seen that before? Have you ever seen, like, you go to a website and it gives you an error and says, like, this website's not there, and you see a special number code? This is the same thing. So 200 was like, everything's okay. We get the words. I'm just going to jump through this bit. So this is like an unstructured version of this. So that's just a big, what we're doing is split. Split will go through this big vector of strings and split it on the spaces. That's what it's done, to turn it into words. Sorry, I got the question online. Is there something you did between data and data body? If you got something different, it either was you consumed the message already and it's gone. So when you do the string on it, it'll be not there. So that's why I had to go back and do it again. That wasn't clear on the lecture notes. Clear on the recording. So that's cool. You got a big list of like 900,000 words. Cool. Maybe we want a bit more structure though. So we can do this guy again. And instead of text, we can get it as a JSON encoding. This is this. And we have to parse this into a JSON object, parse this JSON object. And what you end up with is a special data type called a dictionary. Dictionaries we'll come back to again, super useful, very flexible data format. Yeah, what do I want to do? So what we're going to do here is, I just think this is kind of cool, and then I'll crap on a bit about useful application of this stuff. So basically, we can go through all of Shakespeare while we're waiting here, count the number of words that occur in this length of time, and go through all of Shakespeare's and go like, it said king 1,698 times. It said love 1,279 times. It said man, blah, 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 blah. Really fast. Computers are super fast. Someone's life works. We can summarize it. I wanted to do a little bit of a sidetrack and talk about why you would be interested in doing something like this. And the application that came to my mind is like, it's like, I'll leave you. Has anyone done a course on machine learning yet? Or is it brand new? So I can do that, and that's interesting. So one of these problems that plagued the early internet was spam for email. And you have this problem that we have this unstructured text, like an email message can be however long. And how do you determine if that's spam or worthwhile? So we have this encoding problem. So like, there's a pretty straightforward way of like going like, I just wanted to chuck Bayes' theorem up on the board because it's like most of these things, the natural way to think about it is Bayes' theorem. It's like, I've got two classes of stuff, like say A is going to be, I want to know if this document belongs to the category spam or it belongs to the category Shakespeare. So that would be the probability of A. So say A is the probability of being, this thing is a message I want to keep, I want to throw away. And B would be the data. So like, what's the probability of getting this thing given the data? And Bayes' theorem is like a natural way of developing these statistical algorithms, more or less complicated, but you flip it around and you go like, okay, what's the probability of generating this data if it was in class A or in, you know, if it was Shakespeare or spam, multiplied by the probability, some prior probability I had that it was Shakespeare or spam, and then divided by the total probability. So that's Bayes' theorem. Cool, that's like a little thing you can write down, but then actual implementation of this is kind of hard because it's like, if you think about this term, it's like, okay, I need to know something about like, what's the probability of getting this particular email message, which is a very high dimensional thing. So if I think about any text document, it can have a length, it can go from, you know, any size basically. So you've got to cut down the dimensionality of the problem to something you can work with. So a really, really easy thing you can do, which is one of the first things they did, is something very much just like this, where you go through a corpus of text and you go, I'm just going to pretend words come out of a machine and I'm just going to count frequencies of words. So like, this is really simple. I can get like the top N words I saw in Shakespeare, which is these guys, like, here's the top 16, you know, or whatever. This is just some random word list, but you go like, if it's Shakespeare, you know, the probability, if you want to turn this into a probability, like you'd apply in Bayes' theorem, you'd go like, I saw King 1,698 times out of 900,000 words. So that's a frequency you can get. And just pretend you get all these things one after the other. So that's a really simple feature vector, we'd say, in machine learning land of like, I'm going to go, okay, I'm going to take this text document and embed it into a little vector, which is just counting frequencies of words. And then, well, that's an easy thing. Then I'm going to be even more dumb and going to go, these word frequencies are completely independent of each other. So you have this other problem of dimensionality where it's like, if I have lots of these, so B's I've split out into just like a count of words in a bucket. If it's of class Shakespeare or spam, you know, what's the probability of getting 10 out of 100 counts of King? What's the probability of getting 5 out of 100 counts of Prince? What's the probability of getting blah, 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 Macbeth, say. There's this, like, you can make an assumption that all of these things are independent. Like, you know that it's not independent, like words will occur together. Let's just pretend they're not, and then use that to make a classification algorithm. And this was super successful. And this was how all early spam filtering worked. So that's why you would do something like make a dictionary. I just wanted to show you guys, this is like early application, hopefully not too intense, but it's really simple. You just do this really dumb kind of simple thing where you go, I'm just going to count words and pretend they're independent. If they're, learn it from a corpus of text. So you go, here's good text messages, here's bad ones. Shakespeare will have Prince Denmark, spam will have Prince Nigeria. Done. Any questions on that? Okay, I think that's a good time for a break because I went a bit longer than I wanted. Any questions? Okay, I'll stop for a little bit, then I'll come back. Yeah. Okay. I can actually come to that. Oh, no, that's fine. What you need to do is. Okay. This one. Yeah, I know. That's fine. We start like perhaps out to work before and
Experience for that reason. So it's a bit. Yeah. I'm still seeing that. I'm still yeah. We need a lot of there's very stuff that it's not so like it's yeah like you just like it's hard to put the people in. It's only one of them. I have to keep I'll stay on that. Stay on. It only got I'll talk about it in my I'm trying to get to how much stuff I can tell you about. Sorry. I don't have to see security. I'll get it for you. You won't share anything.
Okay, everyone good to go again? Okay, I'm going to get started again if everyone's okay. Everyone's okay? I'm going to start talking anyway. Cool. All right, so we finished section 1. Hopefully that was interesting. If not, too bad. We're on to the next bit. So, okay, as I said before, first bit was just like a teaser. Here's some stuff, here's some syntax, here's some weird maths things you may or may not be interested in. Might have seen before, you might not. Little gentle introduction into how you might come up with an algorithm for a particular mathematical problem you have. Introduction, bit of a baptism into the Julia syntax. You'll see some stuff. You can try some stuff yourself. As I was saying in the break, though, the only way to learn this stuff is to do it again and again and again. You got to try and do stuff. I would encourage you to the best way to learn is to try and do something you're interested in. If you have a particular maths problem, I don't know where you are, some of you are going to be second year, some of you are going to be a bit later. Even if it has nothing to do with maths, if it's a personal interest, some people really get into visualizations, you can make some really cool computer graphics stuff. The maths behind doing that stuff is super interesting. I know lots of people who've gone down that road. Slightly strangely, a good friend of mine worked with someone who won an Academy Award. So he was just a PhD student working on an open source project with this other guy who worked at Sony DreamWorks, and somehow he knows him really well. It's very confusing. Anyway, that's to get into a little project, do something yourself, try and automate something you do. So if you have a little thing you got to do all the time, see if you can work out how to script it and save yourself a bit of time. That's the best way to learn, is to try and do stuff. Just try and do something dead simple. Get practice. Yeah, so that's the basics. We're going to start going more onto, this is a little bit like if you did a typical CS undergrad, you do some algorithm analysis. We're going to do a little bit of that. I'm also going to talk at the end about tooling. So this is professional development stuff. So you'll see me with this funny thing over here using VS Code. Don't have to use VS Code. VS Code's easy though. It's kind of one of the better ones at the moment. It's free. It's free. Why wouldn't you use it? I'll talk a bit about why you'd want to use a particular IDE over another one. I'm going to talk about Git, GitHub, 2 different things, where they come from. I'm going to talk a bit about Unix, where that comes from. All that stuff's interesting. I'll also talk a little bit about software licensing. That's the section 2. It's going to be a little bit on algorithms and then a little bit on the practice of doing this stuff and the tools you're going to use every day if you do this stuff seriously. People who do software development for a living get really, really fussy about their tools. I guess, I don't know where that comes from. It's like writers, if someone's a novelist, they get really obsessive about getting a special typewriter or something they used to in the old days. Software developers are kind of the same, where they get certain type of software developer gets really obsessive about their tools. I work with people who spend lots of money on mechanical keyboards, if you've seen those, spend $400 on a keyboard. Oh my God, you get the cheap plastic one for $20. Well, I wouldn't use that, but they really like it. They make a nice clacky sound. I don't understand. Anyway, that's where we're going. So we're going to talk about sorting, and I'm going to have to put this huge caveat out the front, right? I don't care about sorting. Sorting is kind of boring. And the first algorithm I'm going to introduce to you guys is the worst algorithm. It's not the worst, but it's very bad. Don't ever do this. It's an educational exercise. This is a huge caveat out the front. If you go and do a job interview and they go, oh, please implement sort, and you crank out bubble sort, it's you're over. So what this is a didactic thing. It's like I'm trying to show you guys this is how an algorithm works. This is how you'd analyze the runtime of an algorithm, understand how efficiency works. Then you'll see better implementations and hopefully understand. This is why I gave you these sort of leading questions when I was going through with the binary adder. Like if you think about addition, it's linear. If you think about multiplication naively, it's n squared. Linear is okay, n squared, not so much. So, and you think about how these things scale. There's actually a hierarchy of scales. I'll talk about that in a little, and you kind of end up at the worst is exponential scaling, where it's like that factorial thing where the problem just grows and grows and grows. Again, I gave a little leading thing talking about machine learning. It's like central problem of machine learning is how do you deal with very high dimensional spaces? How do you do that on a computer in an efficient time? This is the kind of thinking I want you guys to pull out of this when I'm talking about sorting. Sorting is just a simple, boring example. But I got a question about P versus NP. I'm not going to talk about P versus NP in particular, more about problems that scale very, very badly that are typical of NP problems. So Blake in the chat. Yeah, so there's typical problem. There's like a bunch of classic problems that are very, very hard, but very, very useful that scale very, very poorly. So if you want to be a millionaire as a mathematician, you come up with a good solution for one of them. Don't tell anyone how you did it. Make a bit of software, sell it to all the BHP and Commonwealth Bank and all those people. And you make lots and lots of money. In theory. In theory. So sorting isn't interesting in itself. It's just simple, right? And this first algorithm I introduce comes with a big warning, is that it's bad. And what I want you to take out of this first bit is, why is it bad? And it's basically about how things scale as the problem gets bigger and bigger. Kind of have to be like, you do have wins when you're actually working in this stuff. If you're a mathematical developer of like coming up with a better algorithm that you can go from something that scales very badly to something that scales very well. Doesn't happen very often. The more common cases, you should look around for one that someone else has done that's better. That's the usual case. Sometimes you get to be clever and do something better. So, sorting. So this is really simple. We've got some data. Data equals 1, 2, 3, 5, 4, 6. Okay, so it's a really natural problem. So strangely enough, because it's a really common problem, you're going to see it. You're actually going to have a really, really good implementation in base. So you don't even need to do the stuff we're giving you. Like, there's a very, very good implementation in base, Julia, because it's so useful. I'm trying to say if this is a true statement. I don't think I've ever had to implement a version of sorting myself. I've had to implement a priority queue, which we'll talk about a little bit. That'll come back up later on when I'm not sure if it's Andy or Yoni doing it, but that will come up later in the thing. I've actually done my own priority queue in my professional work, but which is kind of like sorting. So it's not one that comes up, but it's like sort of like expected knowledge. You should know how to do this. It's like, so there's a very good one. You can actually specify, if you look at the call signature here, it's like, it's got an option for the algorithm you can use. It's got this funny LT equals is less. So again, this is a named argument. So big hint that this is the thing. It's called LT would be less than. It's calling this funny thing is less. By equals identity and rev for reverse, like whether you want it flipped backwards or forwards. Is less is useful to know about. So this is if you have two types, test whether X is less than Y according to something. So this is a useful function. This is actually the base thing. If you're doing any of these inequalities, it will default down to is less underneath. Flip the sign around if it's a greater than. Cool. So it's going to sort it by is less. So if you call, I can't remember what I called this array, data. If I go sort data 1, 2, 3, 4, 5, 6. If I go rev equals true. 6, 5, 4, 3, 2, 1. Blah, 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 blah. So how could you implement? Has everyone seen? Has anyone done sorting before in another course? Is this new, or who is this old for? I guess would be the smaller set. You've done it before. You've done it before. Oh, that's good. There's only 2. So this would be good. So how does anyone want to, but apart from people who've done it before, like what's the strategy you could use for sorting an array? What's the first thing you would come up with? Does anyone want to have a guess who hasn't done it before? No, no one's brave. That's fine. I wouldn't be either. I remember sitting, oh, yeah?
I can't really how the bubble sort works. So maybe it's the cheating bit, but you can look at the pairs and see if the one on the left is bigger than the right. If they are, then just swap them and just keep doing that for all the pairs until eventually
Yeah.
it's just semi-motor.
So we'll think that's exactly what this code below does. Yes, good. This is called bubble sort. This is like a classical bad algorithm for sorting, right? I think that's a bit harsh because it's like, it's really hard to come up with this stuff. Like, it's really easy with hindsight to go, it's crap. You know, there's other things that are better, but to come up with it in the first place is really hard. And to come up with something even better than that is hard and still active. So you're exactly right. What you could do, we can just look at this array. We've got data. We can scan through this array one at a time, go from 1 to 2 to 3 to 4, and we can test whether the next one coming through is going to be in the wrong order. If it's in the wrong order, we can swap it, go all the way to the end of the array. Does that mean doing one sweep through of that, sorting algorithm, does that guarantee that it's going to be sorted? No. So you have to do it again and again. So I just got a question there. Is there a way to see all the possible algorithms you could choose? It's like, no, the space of algorithms is infinite. So like, that was a question in the chat, like, could you even enumerate the algorithms? So that's, oh, the algorithms you can choose. Sorry, I misunderstood your question. I think you thought it was like, is there like a meta search for sort? Could you sort sorts? Yes, I think the way to get that one would be going to the docs, and it will say, it'll probably be like the defaults will be quick sort, merge sort, maybe heap sort. I'd say look in the Julia docs for the algorithms that are supported. There'll be a small set because like basically quick sort is the winner. I think might be tim sort in Python these days, which is a weird hybrid version, but talk about that later. Pogo sort is the best sort. Do they do linear sorting using hash maps? I'm not sure if there's one implemented. I guess, yeah, that depends on your type, and knowing something about the distribution of data is the other thing. Anyway, so that's right. So going one sweep through, you're not guaranteed to get them in sorted order, so you have to do it again. So let's just copy paste this guy and verify that it works. So little short side note here. Does anyone notice this exclamation mark? Has that come up in the notes before? No? What exclamation mark means is that it's not enforced by the language, but it's like a style thing that what I'm doing will modify the input. So like, I'll just show you because that's easy. So I've got data, 1, 2, 3, 4. I'm going to make a copy of this. Copy. Okay, so if I go bubble sort, data, cool, it sorted it, printed it out. Now data itself is actually modified. So now it took that array and edited it. So this little syntax thing is just a convention. It's not enforced by the language. It's just a hint that when you're doing a function, you're being nice to someone else who's going to use your function, that this thing's going to modify the input, which is a thing you can do. Sorry.
Is it entirely optional, or does it have any effect on the functions the same name like the type?
It does nothing. It's just like, it's like if you call bubble sort like that, that will work too. And it will modify data and no one will know. It's like, it's fine, you can do it. So it's kind of annoying because yeah, that's just the thing. So when you see that, it's a hint that this function is going to modify the input. Depending, this will come up later, but I'll give you a little hint. Some data types can't actually edit. Like if it's a mutable is a function that is in Julia. Basically like returns true if the value of v is mutable. So like, oh, let's see who wrote this code and see how well. If I try and bubble sort 1, it won't do anything, but it also won't, because you can't, these base data types, there's is-bits types, they're called. There's some data types that are not mutable. So you try and do that thing and it won't do it anyway. But arrays are mutable. So if I have this as an array, it's true. I'll give you a little demo of that later, but I just wanted to say it so you know it. Anyway, the idea is that this little exclamation mark is like a warning. I'm going to modify this input. It's not going to be the same as it was before it went into this function. We're going to get the length of A. We're going to stride through from I equals 1 to N. J equals, I got to edit that so I can look at it. For J in I to N minus 1. So you're just going to swoop through once, swapping as you said, easy as, go through again, swap, 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 swap. Really simple. This little bit of syntax is weird. You're going to take J plus 1 and Aij and stick them into Aj plus 1. So just take them, swap them. Make sure you get those pluses and that the right way around. Cool. So that's really easy. How fast is it? So when you, I guess it's in part of your, like, I think one of your questions is like running time of bubble sort. It's like, so this will be gold for you guys if you go to do it. Like, you got a bunch of timing tools in Julia. If you're interested in like how this thing scales, because that's a really natural problem. It's like, if I go data equals rand 1000, one of the things you might want to do is time it. So you can, there's a really simple one you can do is this @time macro. This will actually just take your code and time it. It's a little bit of spew at the end there. So if you want to suppress the output, a little semicolon, it was faster the second time because it was already sorted. That's a hint. So we've got data, time it, 0.00. That's pretty fast, 1,000th of a second, who cares? Is this going to get worse as we get bigger? Yes, it will. So 10,000, bubble sort, it's getting to 0.16 of a second. Do I dare go that one? So chug, 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 chug immediately. So kind of like, oh, wow. It was fine for 1,000, kind of fine for 10,000. Now it's going crazy. Little hint for you guys. If you're on Unix, you might want to start looking at top and going like, oh, is it actually running? You can see Zoom is, oh, it's finished while I did that, of course. Of course, it finished while I did that. But in Windows, it'd be like looking at system monitor, like, did this thing crash or is it just hammering my CPU? So we should be able to see that. If I make it, I'll do it again. Jump across. Top is a little useful tool. You should see Julia sitting there. It's going, my CPU's gone to 100%. Zoom's in the background. I'm always kind of scared doing these demos where I hammer my CPU because Zoom's running and I might crash Zoom and then that kind of defeats the purpose of doing the lecture online, but it's always a little bit scary and I cross my fingers. But it's a useful tool because like one of these things is when you do these big things, you go like, oh, is it just hung or is it like doing something very, very slowly? That's useful. It's also useful to put in a little bit of debug logging so you can see what's going on as you go through, like a counter or something like, oh, I'm up to iteration 1, 2, 3, 4. So like maybe something useful would be to go in here, function, in here, at info, file in, this will be bad. Data. Won't do a big one. Oh, it's too fast. Anyway, you can see that it's gone through and it's putting through something like a progress. You probably want to do a mod in there and a little test so you're not doing it too often, but seeing something about the progress, putting in some print debugging will be very helpful when you're actually going to do your assignment, trying to work out why the hell is this thing not working? Why is it just hanging there? Cool, so that's time. You can also, if you want to capture that, I was just doing that one. Another thing you can do that's kind of useful is use the timed macro. You can go x equals timed, calling it with all that stupid logging. So now x has some extra information in there. You can get time if you actually want to capture that and return it to use it in something else. Like if you want to do a bit of analysis, like say, imagine you're trying to show some sort of scaling or some sort of thing you're going to run and you want to run lots of different cases. You might want to capture the timing. Yep.
So books you can create which time specific events.
Yeah, I'd look through the time documentation, but like you can do TikTok kind of things. There's a whole bunch of stuff you can do. If you're going to get serious though, I would recommend using benchmark tools. Has this come up for you guys? Have you seen this one? This one's more serious. So you would have seen this problem. Oh, I haven't installed it. I'll just hopefully this, fingers crossed, this works while you guys are watching. You know, when I was showing you the other day, I was showing like, oh, here's the plot, and it took ages to start, right? That first bit of pre-compilation is not interesting. What you're interested in is if I run this again and again and again, how long is it actually going to take? Not the first time I run it. Benchmark Tools has a macro called @btime. And again, macros, you've got the same thing. You can ask for help. It's so similar to the time macro, but it executes the thing and it actually, I think it reruns it a few times. So it's actually more serious about how long it takes. So if you're trying to be super careful, use btime and look up benchmark tools for exactly the question you're asking about. If you want to be serious about like instrumenting everything. I got a question up back. Yep, Control C. So like if you're going like that, oh no, what's Paul done? Oh no, oh, that's going to take a while. You can just Control C, interrupt. If it's like really, really bad and it's like, it's not so bad if it's using all the CPU. A bigger problem is if it's using all your memory. It's just like if you haven't done much programming, it's like a much bigger problem is memory use usually, practically. Like what will happen is there'll be like some sort of resource manager in your kernel or like whatever system you're on, and it will just like, if you're lucky, it will just kill it. And the program will disappear and the Julia session will disappear. And you go like, oh, that's weird. If not, it might start swapping on your hard drive. Like it'll write bits of memory to your hard drive and your whole computer will become unusable. So I don't know if has anyone done this? Is that a thing? This is like my day job of doing this, of like running a thing and like, oh no, it's eating my computer. Control C, Control C. Yep, that's what it's like. Yeah, so you know, we're talking a lot about timing, time complexity, space complexity is actually a bigger practical problem in real life. Time is that there's like, get the scaling right, you're fine. Sometimes you just got a lot of data and you have to deal with it. Not so much in this course, I hope. You might run into it accidentally. Biggest one would be like you try and allocate a giant array. Like if you're doing something programmatically and you're going like, I want to make an array that goes from 1 to n, and you accidentally did big int n for your factorial, you know, just before that, and it's a giant array, that will be the sort of thing that will crash out your computer. Does happen all the time, to me anyway. Okay, so timing. So what we're interested, so yeah, it comes up in the notes just after I said it. So there's benchmark tools, link to that repo. Starting to introduce you to Git. I was going to say JIT, but JIT is just in time compile. To Git. One of these things that you'll notice is like when I did that using benchmark tools that went and did some internet stuff and pulled some stuff down, each one of these Julia modules is actually a little Git repository on your computer. So that's how Julia manages its packages. Its package manager is based on Git. So it's like all integrated. Again, it's all open source. If you want to see an example of, like, if you're trying to learn, that one, a really good thing to do is to go and look at people who are really clever and do this stuff, how they implemented it. You can go and have a look at how benchmark tools is implemented. Yeah, and if you're lucky, you can go and click on the docs. And if they're a nice person, they will have written some really lovely bit of information for you. It's got this funny histogram frequency thing. So like you can do all sorts of pretty things if you want to make like nice analysis. When you're a software developer doing performance critical code, you end up spending a lot of time benchmarking. So it's good to learn about. Cool. Don't know how off-piste I went there. Okay. Anyway, if we're just going to be lazy, we can do something like this do timing function, which is just a bit of print debugging using the at time macro. And we can see how this thing scales. And we basically just did this. It's like, as this thing grew and grew, we saw that the runtime started to blow up. So you know, it's this idea that, you know, if you're getting above like 10,000, you probably really, really don't want to use this sorting algorithm, depending on your application. In general, don't use it. Okay. Now, this is like dangerous, but I'll show it to you guys anyway. It's like kind of like slight misgivings about this guy, because like if you're trying to write performance code, doesn't matter for what you're doing, but it's like this is super dangerous, this inbounds macro. It's kind of a hack in Julia to get a little bit more performance. So what the idea is like Julia is a very safe language. It's hard to shoot yourself in the foot. Like if you're going to something like C, you can read bits of memory you're not meant to read, and you can do all sorts of things. You can iterate out of arrays. This is actually what this will do, this macro, is it will turn off bounds checking for an array. Sorry, I didn't put a question mark there. So what inbounds will do when you're iterating over an array, it will go, you're going to index into this array. I'm not going to check before you do that whether you're allowed to do that. Like if you have a 10 length array and you're trying to index element 57, that's like a thing you shouldn't be allowed to do, right? But if I ask you nicely and put this inbounds macro, Julia will let you do that to your own detriment. But if you're trying to go faster, this is the kind of stuff you do. You turn off bounds checking to go a little bit faster. So we've got bubble sort and slightly faster bubble sort. There's a bit of type annotation here. So what we've got, you know, you don't need to do this. Again, like I highlighted this last time, is like, you don't need to do this. You need to do this for when something called multiple dispatch comes up. I may or may not introduce that to you shortly, depending on if you're interested. It'll come up later. Andy will probably be the one to introduce it to you properly. This is just saying it's a vector of integers. I'm going to do this on a vector of integers, and I'm going to return a vector of integers from the function. That's the stuff on the outside. You could also take that ... vector int and stick that on A as well. That'll work. Don't need to do that though. So what this one is though, is it's this inbounds macro. So what this will do between begin and end here is every time I look into this array, I'm going to check. I'm not going to bother checking whether I'm allowed to do that or not. So if you write this yourself, please be sure that it's okay to do this. And be really careful about the bounds, otherwise the whole thing will crash. Segfault, I won't demonstrate for you, but not a good thing. So yeah, just basically, if that's not clear, so if I go data equals a 10 element array, if I go data 11, you get an error. Do it. Oh no, it stopped me doing that. I'd have to do a begin end. Oh, let's just try it. Oh, I won't. Anyway, has to be in a begin, has to be bound. Okay, so that double turn off bounds checking. What that will do is that you'll get a slight boost in performance. I'd be surprised if it's significant though. So because of this now, if I do slightly faster bubble sort on data, because I've got this type annotation on here, anyone want to guess what will happen? Does anyone remember what data is though? Because I'm just generating it. Data is rand 10. So that is a vector of float 64s. If I try and call slightly forced on data, okay, no, not allowed to do that because it only works for an array of vector in 64. Because you've given me a vector of float 64. No, not allowed to do it. Here's a thing that's close to that, but I don't know anything about that. Let's fix that by just getting rid of the type annotation because it's just restricted what we're allowed to do with this thing. There's nothing about this that says we can't do it for all types of numbers. So, cool, that will do. So, let's time them and see. So we'll make these bigger ones. What was the size we were saying? 10,000. Data at time. Bubble sort data. Oh, I've got my logging in there. I'll get rid of that. Okay, that was silly. Data. Okay, at time bubble sort took 1.9. We do data again. And slightly faster bubble sort. So it'd be a bad name if it's not actually faster. It's really just slightly faster. So we went from 0.2 of a second to 0.15 of a second. So it's reduced if you think about this as like functional stuff, it's kind of reduced the coefficient, but not reduced the scaling though. So if we make data even bigger again, it's still going to get slow in the same kind of way. Again, chug. So still scaling badly. Like it's more than 10 times slower for something that's 10 times bigger, hopefully. Cool. Yeah, it's really slow. Okay, so you can do this. I'm going to kill that because someone asked. Oh, wasting my time. Function, slightly forced. This is kind of, you don't have to put it here if you're going to do this. I can actually remove this guy. And I can remove this guy. And you can actually just put it in the outermost loop. Sorry, I've got to tidy stuff up as I go. You can just put it around here at inbounds. It will do the same thing. So the macro will apply for all the things below that in the loop. It'll turn off bounds checking inside. That should do exactly the same thing. Should work. Should be about the same time. If you don't want to do the begin end stuff. Okay, so that's this kind of dirty trick. Actually, there was a question on Ed about someone saying, you know, the example in the homework was way too big. Like I think it said to do it to 10 to the 8. And someone was going like, that's crazy. It's going to take like to the end of the universe for that to finish. He's like, yes, don't do that. So I got a little bit obsessed yesterday and I went like, I can do it. How big can I make bubble sort go? It's like, I've got an AWS account at work. Can I rent a really good computer and see how big I can make bubble sort work? I thought, no, that's how you lose your job for. So There's the dirty software engineering tricks about how you can make these things faster. I'm sure you could be really clever with allocation. Talk about this a bit later, but one of the things that tends to make algorithms slow is when you allocate memory. So if you can make a version of this that doesn't allocate any memory, you will win big. That's the way of winning big. Shouldn't be a problem for this particular one anyway. This will come up again, like if you're looking at the implementation we do of merge sort, that will be a definite optimization you could make. You could do a non-allocating version. Cool. Where are we up to? We got up to 22. So it shaved a few milliseconds off compute time, but it's not a big deal. It's like it's still scaling badly. So it's not so much about percentages. Like if I make something 20% faster, I'm not happy. If I make something an order of magnitude faster, I'm happy. That's the kind of thing you want to be aiming for. So like, has happened. Like I had it recently at work. I had a thing that I managed to make 4 orders of magnitude faster by doing a magic trick. But the difference was I traded off an exact algorithm for an approximate algorithm. But the difference in the error was very, very small, so I can get away with that. They're the kind of things you want to go for. So what we're going to do is we're going to do some dirty timing here. Again, this goes exactly to your point. Here's a really simple way of instrumenting timing. You can do something here. It's like time nanosecond. We've got start time is going to call time nanoseconds function. Again, you want int. That's going to give the time in nanoseconds. Think about nanoseconds and how many nanoseconds can you fit in uint 64s? It's probably a hint in that log message. Like,
5.8 as well.
yes, that's right. Clever reading. This is actually a problem in my day job. I do stuff to do with LiDAR. And LiDAR is one of those applications where you need to worry about millisecond precision for time. LiDAR is time of flight lasers range finding. So what the sensor will do is it will send out a pulse of light, start off a clock, measure it, come back. How far is the difference in time? If you're measuring something like from here to that wall away, it's like very, very quick, right? So you need a clock that's really, really fast. But if you're doing things in nanoseconds, you can't just be dumb and just go, this is the time from here to, next week or the week after, because you run out of room. It's like, you can very easily run out of precision. So you need to have this staggered hierarchy of times you're tracking. Yeah, it's real. It won't be accurate on a real computer. This is another one where I'll say a little bit about, we've got the reality of these computers and what they're doing, if I ask it the time, it does other stuff in the background. You're on an operating system that can run lots and lots of programs at once. The actual timing is very imprecise, like down below microseconds anyway. You need specialized hardware to do specialized timing. Even though it will say a time in nanoseconds, the accuracy on that is very much not nanoseconds. That's a conversation for another time anyway. So what we're going to go through here is we're going to run through this do timing function. We're going to run through a range of sizes. And for n in n range, we're going to generate some random data with a random seed, so it's deterministic. When I was doing my timings before, I wasn't using the same data. So let's make sure we're using the same data, be a little bit careful. Start time, end time for bubble sort. We'll push this into an array of times. We're going to get the end time minus the start time to turn into milliseconds. This int will be, because if we do this division, it won't necessarily be, let's just do that. Start time equals time ns. End time equals time ns. So we've got 2 times there. Type of start time should be a uint 64, I'm guessing. That's where the 5.8 years comes from. If I actually evaluate this little expression in here, I don't know why the int's there. Anyway, you don't have to actually do that int. But the int, I think the brackets are in the wrong spot. Yeah, the brackets are in the wrong spot there. That's unnecessary. Should just be able to do that. That'll be the same. Yeah. Oh, bug in the code. In the lectures, you don't need to do that. Maybe if you wanted to round this, you go round int this guy. If you wanted to have it in, if you want to see how to do that. Basically, it's going to push to an array. So if I have an array, a equals blah, push a2, and you see it's got this exclamation syntax because it's modifying the input to 4. So like if you have this is typically the case, you use this method when you don't know how big the array you're going to make is going to be in the end. You can't pre-allocate it. So you're just going to go, oh, I'll just push to it as I make it. Not the most efficient thing to do, but it's very practical. So if we run this code, I might try and run it and see what it does. See if we get the same thing as the notes. Hope that's clear what this thing's doing. Because I'm including plots, it's going to be slow for the first time in this session. We're going to run this timing thing. It was super fast because we're only going up to 10 to the 4. And let's see how this goes. If I plot, this is probably useful to just look at how plots work. You know, you can see a bunch of things. So what I'm going to do is the x-axis is going to be the n range, which is this. I probably don't. Oh no, that's on the outside. It's defined inside and outside. That's a little bit silly. And the times, and it's going to put an X label of input size, a Y label of sorting time. Legend is not going to be there, and the shape's a circle. So it'll be a little bit slow. Always slow for the first time for plots in Julia. I should have cheated and done this before I came into the lecture. So, okay, so we've got a plot. I got a couple of questions in the chat that I was ignoring. So, how do computers measure time? What sort of components are manufactured to do that? No, down a second. So, the clock speed in a CPU itself will be in gigahertz. So, it's a clock that's running at 3 gigahertz with a 3 gigahertz thing. So, you can use that. But it's a bit of an abstraction to say this block of code when it thinks the time is the actual time. Yeah, there's a whole thing about like precision in time I won't get into. I could talk to you for hours about that because I do stuff with GPS, and it's like one of these problems is like, how do you actually measure time? It's like a huge technical thing, and it enables you to do navigation. Like if you're doing GPS, again, you need to know nanosecond precision. And funnily enough, hitting things, the most accurate clocks around that most people have access to these days is a GPS receiver. So if you have one in a smartwatch or your phone, the clock on that will be accurate to about 14 nanoseconds, believe it or not, because of what it has to do to solve for GPS positioning. Yeah, cool. That's about timing anyway. So it kind of does do timing itself. It is a clock, but because of how operating systems work, a CPU, any timing you do on a outside of the CPU, it'll be fairly inaccurate. How do you make plotting more efficient if it's taking a long time to plot? It should only be slow the first time it is to plot. If it's taking a long time, you're probably trying to plot too much stuff. To Alex in the chat, like apart from that first time to plot, if I plot this guy again, it should be super fast. Like it's fast. But if it's taking too long to plot, you're probably just putting too much data in the plot and you need to thin it out. This would be the usual answer. So like don't plot every point, just plot a few. Anyway, sideways and sideways. So what does that look like to people? How is that scaling? Anyone want to guess? What kind of function would you guess for that, for the scaling? Sorry, speak up. Probably, so squared. Some polynomial scaling. Yep. How would you empirically show that? Like what would be a thing you could do? Has anyone got an idea? Yep, that's right. So in the notes, I think we do exactly that, hopefully next. So I don't think I've added these two guys, but there's a package here for general linear models. and data frames. Data frames are really useful. These will come up again and again and again. If you used pandas in Python, you will have seen that. Kind of the equivalent for Julia is a data frame where you've got tabular data in a big table. So what we're doing here is we're going to take the data, put it into a data frame. So I haven't added these guys because I didn't think I'd get to this point in the notes so quickly. That's okay. So these will have to get added. I'll talk about it while we wait for that to finish. So what you're going to do is we're going to take as the X data n range and Y the times. So data frames is going to come back. This is just like a nice little container for tabular data. Yeah, you'll see a lot on that. It's super useful. I wish I'd added this before. What we're going to do though is in GLM, there's lots of ways you can do this though. This is just one way, like you can do it by hand and I'll show you how to do this if you want to. But if you wanted to fit a linear model and use a package, you can use GLM. It will fit a general linear model. It has a formula macro where you'll give it the form of formula and the data, and it will fit a linear model. So it's linear in the coefficients if you haven't done least square stuff before. It's going to fit an A, a B, and a C to this model and tell you what they are. So that's, I don't know, what do people think about that? Is that compelling? Does that show to you that it is scaling like this or not, do you think? If we're fitting a regression model, is there a problem with doing that? Anyone see anything? So if I take, oh yeah, go. Yeah, so this is like, again, I was saying a little bit about machine learning. It's like, okay, cool, a quadratic fits this data well, a cubic will as well, a quadratic, a quintic will as well. Any higher order polynomial will also fit this model very, very well. There's this general problem that as I add more terms to my regression model, I can always fit the data better and better and better. Am I allowed to? Actually, a really sophisticated question. So like, not going to answer it here. Model selection in statistics is a big problem, but this does some nice stuff for you. It's going to go, okay, what's the intercept? What's the slope? What's the coefficient? Small residual. Fantastic. Gives you a p-test, says, yeah, it's super significant. Does that mean much? Maybe, maybe not. Again, model selection is a problem. Cool. So I won't go through that too much, but they're in the notes, similar data, slightly different. Yeah, so again, another one question thing is you're only fitting the observed points. So it's like, what do you do about stuff you've never seen before? How do you know that your model is going to be robust to new data you're going to see that's going to come along? This is just a hint of the problems you have if you're doing machine learning for real. It's like, this is like the whole problem of making this stuff work for real. But you can see it's like as an eyeball fit, it's like, yeah, cool. Quadratic model looks pretty good. It has a small residual, fits pretty well. So, we can like this unobserved data points is like, we can easily generate new data and see what happens. So next bit in the notes would be like, okay, let's make a point outside the range of what we fitted and see how well our fitted model predicts new data. Which is the next bit. It's saying, if you do that, I think it's getting close to time to calling it a close, but if you do that, you go, oh, predicted time is going to be 1 second, actual time's 1.3 seconds, predicted time's about 3 seconds, actual time's about 4 seconds, but, it's quadratic, so your errors are going to grow quadratically too. So you can imagine this thing's going to diverge as you get further away from where you fitted the data anyway. So you could do, hypothesis tests where you go like, is this model good on the new data? Did it fit within my error bounds? Yeah, no, maybe, maybe not. That's a hint. So I think it's time to, I think I'll call it a close there, just to go, okay, it looks like this thing is scaling quadratically. Quadratically is not a good way to scale. It's really easy to get really big arrays. Like, how much memory do you have in your computer? What's a typical working data size? So We had Shakespeare's text. Might be weird to run bubble sort on Shakespeare's text corpus of words, but that was 900,000 words. And that was like a thing, it downloaded almost instantaneously off the internet. So it's really easy. That's not a big data set to run on. We want things that are more efficient. Sorting is a really, a problem that will come up. So getting it to scale better is a good thing to aim for. Okay. Any questions? I'll finish it there. No? Good. Okay. Thank you.